Welcome to This Explainer. Today, we're zooming out, way out, to look at the entire history of science. But we're not just going to rattle off a dusty timeline of dates and names. Instead, I want you to picture this as a massive, multi-millennial relay race. We're tracking a 6,000-year marathon that connects ancient builders shaping mud bricks all the way to modern astrophysicists mapping the unseen universe. It's like a giant puzzle, where every scientist takes the baton of knowledge, runs their leg of the race, and passes it on to the next generation.
So let's dive right in with a pretty fundamental question. When did humanity actually first start doing science? It's a fascinating mystery, really. If we define science as, observing the world, recognizing patterns, and solving problems, we have to rewind the clock way, way past the lab coats and microscopes of recent centuries. We literally have to go back to the very dawn of human civilization to find our first scientific ancestors. To make sense of this epic journey, we'll be tracking our historical relay race across 5 distinct eras. 1. The dawn of early civilizations. 2. Greek and medieval minds. 3. The scientific revolution. 4. The 20th century science explosion. And 5. Modern frontiers in science.
Let's start with our very first era, the dawn of early civilizations, the pragmatic pioneers. Back in this early era, science absolutely wasn't driven by a desire to publish papers or win fancy awards. It was driven purely by the pragmatic, everyday needs of survival, organization, and construction. They had real-world problems to solve, and honestly, their solutions were incredibly brilliant. Think about the number 60 for a second. Every single time you look at a clock, you are relying on a highly efficient numerical system invented by ancient Mesopotamians, somewhere between 4,000 and 3,500 BCE. They used a base 60 numeric system, which is exactly why we still have 60 seconds in a minute, 60 minutes in an hour, and 360 degrees in a circle. It allowed for way easier calculations than previous systems, so you can literally thank a Mesopotamian from 6,000 years ago for how you track your day. And this brilliantly illustrates how early civilizations built foundational building blocks to solve immediate practical problems. Just look at this side by side. Around 3100 BCE, ancient Egypt was already developing a 365-day calendar, inventing a measurement system called the cubit, which was actually based on the length of a forearm, and creating hieroglyphics. Meanwhile, over in ancient India, around 3300 BCE, cities were pioneering advanced urban infrastructure. We are talking uniform baked brick dwellings, grid-like street patterns for easy navigation, and incredibly sophisticated drainage and sewage systems to manage waste and prevent flooding. It was pure practical science in action.
Which brings us to our second era, Greek and medieval minds, the philosophers of nature.
As civilization stabilized a bit, thinkers began to shift from purely pragmatic engineering to deeper theoretical thinking. They started asking not just, how do we build this, but what is the fundamental nature of the universe? Now, what's really interesting here is the dramatic juxtaposition between 2 absolute titans of Greek philosophy. On one side, you have Plato, who posited that mathematics, especially geometry, holds the key to understanding the universe. He believed the physical world was just an imperfect reflection of eternal mathematical truths. But on the exact opposite side, we have his famous student, Aristotle. Aristotle diverged completely, proposing that knowledge actually arises from our sensory experiences in the external world. He argued that we must begin with specific observations and then generalize them into universal principles. These are 2 incredibly contrasting pillars of scientific thought that still influence how we study the world today.
Now, as we transition from the Greeks into the Middle Ages, roughly 500 to 1500 CE, the focus kind of shifted towards systematically compiling and organizing all of this vast philosophical knowledge. A total standout figure here is Roger Bacon. He's famous for conducting some of the earliest crucial experiments in alchemy and optics, and he systematically documented his findings in 3 incredibly influential works: the Opus Majus, which covered math, physics, and philosophy; the Opus Minus, which summarized his greater work; and the Opus Tertium, which he actually sent straight to Pope Clement IV to ensure it wouldn't be lost to history.
Moving right along to era number 3, the scientific revolution, the method makers. Entering the 16th and 17th centuries, the scientific community underwent a profound transformation. The baton is essentially passed from the philosophers directly to the modern observers. Sparked by the Copernican revolution, this era birthed the scientific method as we know it today. Groundbreaking giants like Nicholas Copernicus, Galileo Galilei, and Isaac Newton laid the ultimate groundwork. They forced us past pure philosophy and established systematic observation and experimentation. Honestly, without their rigorous methods, the explosive advancements of the modern world simply wouldn't have been possible. Okay, strap in for era number 4, the 20th century science explosion. I'm actually going to pick up the pace a bit here because the sheer volume and speed of scientific discovery in the 1900s was just completely unprecedented. The race goes from a steady marathon to an all-out sprint. Let's rapid fire through this phenomenal timeline of physics. In 1900, Max Planck introduces quantum theory. Just 5 years later, in 1905, Albert Einstein drops his theory of special relativity and the famous equation E equals mc squared, proving mass and energy are interchangeable. By 1911, Ernest Rutherford identifies the atomic nucleus by bouncing alpha particles off gold foil. And in 1915, Einstein is back at it, proposing the general theory of relativity, completely revolutionizing our understanding of gravity, planetary motion, and even the existence of black holes. In just 15 years, the very fabric of our reality was completely rewritten.
So the absolute crucial point in that timeline, the thing that really kicked it all off, requires a quick definition. And that word is quanta. Back in 1900, Max Planck proposed that energy actually isn't this continuous wave, but rather it comprises discrete, specific packets called quanta. This meant energy could only be transferred in fixed amounts. It was such a radical departure from classical physics that it took years for the full impact to be recognized, but it completely revolutionized how we understand energy transfer and ultimately earned Planck the Nobel Prize in Physics.
But, hey, while physics was exploding, biology was running its own intense, fast-paced relay race to uncover the actual secret of life. Look at this progression. In 1910, Thomas Hunt Morgan is experimenting with fruit flies, proving that genes are arranged in chromosomes and determine hereditary traits. Fast forward to 1953, James Watson and Francis Crick meticulously gather information to discover the physical shape of this genetic code, the iconic DNA double helix. And by 1977, Frederick Sanger and his colleagues achieved the massive milestone of publishing an organism's first completely sequenced DNA. The 20th century wasn't just about the microscopic or the cosmic, though. It was also about understanding our very own planetary ecosystem. I want to anchor us on this vital concept from 1967. Sucrol Manabe and Richard Wetherell developed the world's very first computer model of Earth's climate. This groundbreaking achievement paved the way for a completely new scientific discipline and brought us the early warnings of the anthropogenic greenhouse effect, showing us mathematically exactly how human activity impacts the global climate. And the discoveries just kept accelerating as the century closed out, just a burst of rapid discoveries across completely diverse fields. In 1983, the HIV virus causing AIDS was isolated. In 1985, a completely new form of carbon, Buckminster fullerene, or C60, was discovered. That exact same year, scientists detected a massive hole in the ozone layer over Antarctica, driven by CFCs. And crossing the finish line of the millennium in 2001, the International Human Genome Sequencing Consortium published nearly complete sequences of the human genome. The baton was moving faster than ever before. Which brings us to our final leg of the race. Era number 5, modern frontiers in science, the unseen and the cosmic. That massive explosion of 20th century knowledge launches us directly into the 21st century, where our scientific tools finally allow us to explore the impossibly small and the unfathomably large. Building instantly on that broad genetic groundwork we just talked about, by 2003, we hit a stunning new milestone. The first complete sequence of a cancer patient's genome was published. This is huge because it takes all that previous theory and applies it directly to individual human health, opening an incredible door to personalized medicine and a much deeper understanding of cancer genetics. Now, on the cosmic side of things, in 2006, Maxim Markovech and his team discovered dark matter. And what is truly mind-bending about this, really think about this, is that dark matter doesn't interact with light whatsoever. It is completely invisible to our eyes and to traditional telescopes. It's only detectable through its massive gravitational effects on other objects in the universe. We literally discovered something that makes up a huge portion of our universe without ever actually seeing it. And as our gaze stays locked on the stars, jumping to 2015, NASA's Mars Reconnaissance Orbiter provided conclusive evidence of liquid water on Mars. This wasn't just a fun piece of trivia about a neighboring space rock. It carried massive, thrilling implications for the possibility of life existing on the red planet. To put that into perspective, we went from early Mesopotamians tracking the stars for their basic calendars to modern orbiters finding water on other worlds. The scope of our scientific reach has grown exponentially. Which brings us to the end of today's explainer. But before we wrap up, I want to leave you with a final provocative thought. We've traced this epic relay race from mud bricks and fruit flies to invisible dark matter and Martian water. The baton is now firmly in the hands of today's scientists. So, looking at the sheer acceleration of discovery we've just covered, what invisible, microscopic, or even alien truths do you think the next generation will uncover? The race is far from over, and you know what? The next lap is going to be absolutely spectacular. Thanks so much for exploring this with me today.